All right, so let's take a look at the last unit, oscillations. And I do this one, oscillations last after rotation. Normally I like to do the conservation of energy, but in Physics C, you guys do have to understand how to set up the differential equations when it requires torque on some of these. So simple harmonic motion, oscillating motion as a restoring force is proportional displacement from equilibrium. That's the characteristic of any simple harmonic motion. So, like, that's the definition. There must be a restoring force or torque for rotational objects. A restoring force or torque that is proportional to the displacement. Now, the consequence of that when you set up that kind of differential equation, and we'll remember how we'll review how to do that, the result is that the solution looks like a sinusoid. It's periodic, it has a position, and subsequent the velocity and acceleration, which are derivatives, is going to be some amplitude times cosine of omega t plus v. And then overall, the total energy, kinetic and potential energy, remains constant. Those are very common characteristics for all scenarios. When we derive it, you are either going to use, and this is more common now in the harder AP Physics C exam format, you're going to see more examples of you needing to be able to set up the differential equation and infer what the period is that are not the standard ones, okay? Not just standard pendulums, mass springs, things like that. So when you set that up, there needs to be a negative sign. It needs to have something, a constant squared, and it has to be that same variable there. And if you do that without going into the advanced math and differential equations to analyze it, the solution is going to look like this. Okay, so that's the general process. You're going to do net force equals ma or net torque equals I alpha, and you're going to pattern match the angular velocity. The period is going to be 2 pi over omega, if you remember that from your graphs of sine and cosine back in your pre-calculus days. Okay, so there's a few examples we look at. One is the pendulum. Pendulum period equation is given to 2 pi root L over G. That's because the omega is square root of G over L. If you do a net torque equation here, you would derive that, and we'll go through some examples where we have to derive this part here. But in general, pendulums are only approximate simple harmonic motion for small angles, because in the small angle approximation, we say sine theta is about equal to theta. So this is our small angle approximation. For small angles, sine theta is about equal to theta, and cosine theta is about equal to 1. Those are our small angle approximations that we use when we're setting up the net torque equals I alpha to set up the, if you want to see the derivation. And we've done the lessons have the derivations on how to do that, but that's something that we've done before. The pendulum period is only dependent on length of the string and the acceleration due to gravity. It's not affected by the mass. The maximum height is based off well, at the maximum height, there's no kinetic energy, so we're converting between gravitational potential energy and kinetic energy at the bottom down there. Okay, so that's like the main idea. And you're basically using Unit 3, conservation of energy. Physical pendulum, okay, this is if you did AP Physics 1, we didn't do physical pendulum, but this physical pendulum period is really nice. This is something that's not just a ball at the end of the string. It is maybe a rod with the extra objects, but this is more general case where you have something pivoting and it has some rotational inertia, and the I is the rotational inertia around this pivot. Okay, m is the total mass of the object that's swinging back and forth, and the d is the distance from the pivot to the center of mass. You might have to go back to Unit 4 material and use center of mass calculations to find the center of mass, and then m is the mass of the pendulum here. Okay, so this one does depend on the mass of the pendulum, unlike the pendulum with the ball at the end, and that's because the masses cancel with the ball at the end of a string. So that's how you use the physical pendulum equation. You can derive this by first principles if you want, but there's going to be a lot of multiple choice questions where it's faster if you understand that. Now be very careful that you don't just use the length of the rod. It's the distance to the center of mass. That's probably going to be the part that most people do in not using making a mistake when using this equation. We have horizontal mass springs. That's where it's oscillating horizontally back and forth. The period is 2 pi root m over k, and the spring force acts as the restoring force. Again, there's going to be a conversion between spring potential energy and kinetic energy as we move back and forth in here. Okay, at maximum stretch, you have no kinetic energy, and at equilibrium, when the net force is 0, you have the maximum kinetic energy. You have the greatest force when you've stretched, because remember, the restoring force is proportional to how far away we are. So that's kind of the scenario for horizontal mass spring. Vertical mass spring, Same period equation, okay, still conservation of energy, but there's 3 forms of energy, which makes this one quite a bit trickier to deal with. You have the equilibrium, you have the top point, bottom point. You are converting between spring potential, gravitational potential, and kinetic energy. You always still have the maximum kinetic energy in the equilibrium position, but you have an exchange of potential energy, spring or gravitational potential energy, depending on where you're located. So the restoring force is a little bit different in terms of there's gravity and the spring force. But maximum stretch, you have the lowest gravitational potential. Well, it depends on which we're talking about. At the highest point, you have the maximum gravitational potential energy. At the lowest point, you have the lowest gravitational potential, but the most spring potential. Overall, though, you're exchanging, again, between kinetic and potential energy. It's just now it's a mix of spring potential and gravitational potential energy. Okay. Let's go through a few examples here. So we have a pendulum constructed by attaching a 1 kilogram sphere. So there's a 1 kilogram sphere at the end of a light string. A second 1 kilogram sphere is attached to the end of a spring, also fixed to the ceiling. Both spheres are displaced from equilibrium, and the directions shown and oscillate with the same period. And the period for this is 2 pi root L over G. Period for a mass spring is 2 pi root M over K. Okay. If the 1 kilogram spheres are replaced with 2 kilogram spheres and the amplitudes of oscillations are unchanged, which is true about the resulting periods? Well, the period's only depending on L, so no change on this guy. The mass doesn't matter. But if we increase the mass, go from 1 to 2 kilograms, we increase that value, the period's going to go up. So there's no change in the period of the pendulum, but the period of the spring is going to increase. So that's going to be B. Okay, so a block is hung vertically from an ideal spring. The block is pulled down, released, and allowed to oscillate. The vertical position Y is shown in the graph, which the following best represents the corresponding acceleration of the block. So there's a couple of ways to look at this. We know the acceleration is the second derivative. Okay, so you can look at the concavity, or you could look at it from a physical sense. You could say, like, hey, remember when it has the max acceleration when the velocity is 0. And it has the min acceleration or zero acceleration at maximum velocity. And maximum velocity, like the velocity would be the slope of this graph here, right? So if you look at this, you say like here the velocity is 0 at this point here and here. Okay, velocities are 0. So what that means is the velocity is 0, that's where it has the most acceleration. Now, the second derivative is going to be the concavity. So this is concave down. So we'd expect a big negative number here. So you want a big negative number here like this, right halfway between these two marks. This one is 0, so it can't be that one. This one is 0, can't be that one. This one is positive, can't be that one either. So we already know it's A. Okay, so that's one way to look at it. The other way to look at it is, remember, it's a cosine curve, so the second derivative is going to be, if I have x as a cosine omega t plus phi, the first derivative is going to be negative a sine omega t plus phi times omega by chain rule, and the acceleration is going to be the derivative of this guy. Derivative of sine is just cosine, so it's negative a omega squared cosine of omega t plus phi. And so this looks just like this guy, but upside down, got a negative sign. So we're looking for the one that also looks upside down. That's another way to look at it. Any one of those ways are ways to reason it out as long as you're using the correct principles. All right, so let's look at this FRQ. We have this uniform board of length L and mass M is attached to a pivot at the shown. So this length here is L. The bottom end is attached to a spring with the spring constant K. When the board is totally vertical, the spring end is its relaxed length. The board is displaced a small distance x and released and oscillates in simple harmonic motion. Assume that the spring remains horizontal during the motion and small single approximations are valid. Express any algebraic answers in terms of L, M, X, and fundamental constants is appropriate. Derive an expression for the period. So this is not a physical pendulum. I can't just use the formula for a physical pendulum directly because we have this spring thing here. So we're going to have to derive it the hard way, which is to look at, in this case, net torque equals I alpha when you have a pendulum like this. Right, so we're going to identify our axis of rotation, and we're going to use net torque equals I alpha. Oh, they were supposed to say that the rotational inertia for a rod around the end is 1/3 ml squared here. So we're going to just keep that in mind as we're doing this. All right, so let's identify. So let's say this direction is the positive direction. Well, actually, we'll say this direction, counterclockwise is the positive direction. So this is a negative angular displacement. So keep that in mind as we're kind of working through this. So when we want to do the net torque equals I alpha, what we want to do is we want to draw our free body diagram, right? So we're going to have gravity acting at the center of mass here. And then you're going to have a spring force acting right here like this, right? All right, so now we're also going to have a force from this thing probably up and to the left just to keep the net force. Well, we don't know there's going to be a force from the axle here or the pivot, and we don't know the direction of it. But it doesn't really matter because it's not going to contribute to the torque part, right? Because the torque from that guy is going to be 0. So we do net torque equals I alpha. We want to think about all the torques that are happening here. So we're going to draw our R vector from here to here. This is L over 2. And given this is theta, let's do it in terms of theta here. This is going to be, let's see here. This is going to be, if you look at this, we don't care about this. They're not perpendicular. We care about this horizontal displacement right here. We care about this part right here, right, which is going to be L over 2 sine theta. So that is going to be a positive torque because it would cause it to rotate clockwise. So that's going to be L over 2 sine theta times mg is that torque. And this is also going to be a positive torque from the spring force. You draw the R vector from there to there. That's L. And we think about the, the X here is actually just L sine theta, right? So we'll probably do that in terms of L sine theta. And that's going to be another positive torque, L sine theta. Actually, sorry. No. Take it back. The spring force is horizontal, right? So the distance we care about is L cosine theta times the spring force, which is going to be K times X there. Okay, let's see if we have anything. Oh, we can use K in our spring constant in our answer. Okay, so that's the net torque, and that's going to equal I alpha. Now, technically, these thetas are negative because we've displaced it in negative direction, and we're making everything positive. But this is going to be I times the second derivative of theta here like this. Okay, so we want to use, that's our general setup. Now, a couple of things. We have to make it look like, this is what we're looking for. We're trying to make it look like negative omega squared theta. This is our goal, is to make the equation look like that because that's how we are going to figure out the period. Now, we're going to use small angle approximations. And so these are supposed to be negative thetas, by the way. So negative theta and negative cosine theta. So first off, small angle approximation is sine theta is about equal to theta, and cosine theta is about equal to 1. That's our small angle approximation. Okay, that's why we displace it a small angle. And so this is going to be negative L over 2 theta times mg. And this is going to be about 1, so it's going to be plus L k x. Now, the x we got to put in terms of theta, because that's what we're going to have to do. But we know x is L sine theta, so this is L sine theta, but it's negative. Why is it negative? Because the angle is negative, because really the angle's been displaced in the negative direction. And that's going to be equal to I times d squared theta d squared, like that. But the I, we can replace. We know what the rotational inertia of the rod is. It's going to be 1/3 ml squared. Okay. So this is going to be, let's factor out the negative theta here. And you're going to get L over 2 times mg plus KL squared is equal to 1/3 ml squared d squared theta dt squared. Okay, so we can cancel out. We're going to divide by L squared, multiply by 3, and divide by m to get rid of all of that. And so then what you'll notice here is we have this negative, this quantity here, which is 3. One of these L's will cancel, by the way, so that'll be 1 there. Get rid of that. It'll be negative 3 times mg plus KL all over ml times theta is equal to d squared theta dt squared, like this. So that's our setup. And to pattern match against omega squared, this guy is my omega. My omega is going to be 3 mg plus KL over mg, like that. Or omega squared is going to be that. So omega is going to be the square root of that. And my period is going to be 2 pi over omega, which is 2 pi, and then just flip this guy over, right? 1 over it. So it's going to be mg over 3 mg plus KL, like that. Okay, so that is our equation for the period there. what is the maximum energy of the springboard system during this motion? So let's talk about, we've stretched it. Let's think about all the energy that there is happening. We're exchanging. When we stretch it, we have some spring potential energy. So the spring potential energy at the maximum amplitude, maximum stretch, at the furthest, the spring potential energy is going to be 1/2 kx squared. That we already know. We're going to have some gravitational potential energy. Let assume, yeah, we should make an assumption. Assume h equals 0 is at the lowest point, the bottom of the board. Okay, because you need to do that for the gravitational potential energy here. So if we think about this kind of scenario here, and we think about, let's erase all of this so we can kind of like figure out the center of mass, right? So the center of mass is located here. We're going to have some gravitational potential energy here. So we're going to think about how high we are relative. This is our h equals 0, so I want to figure out what that distance here is. Well, I know this distance is L over 2, and I know this distance is L over 2, let's see, this is theta. This is cosine theta, right? And then this whole distance is L. So this distance here is L minus L over 2 cosine theta. That would be the gravitational potential energy part. Okay. And so we can say, okay, so this is going to be mg L minus L over 2 cosine theta. Now, we're not allowed to use cosine theta. Theta was just an expression to help set this up. We have to do it in terms of x, m, or L. But we know that x is going to be L sine theta, right? Because we know, like, that's what we did before over here, was replace the x with L sine theta, because that would be this distance here, this distance L. So this distance is L sine theta. So that means we can replace sine theta. We know that, so what does that make? Cosine theta. You could do inverses, but probably the easiest way to think about it is like, this is x, this is L, this is theta. Cosine of theta is going to be this, adjacent over hypotenuse, right? So this is square root of L squared minus x squared, but from Pythagorean theorem. So cosine theta is adjacent square root of L squared minus x squared over L. So that's going to go in for that cosine theta. So it's going to be mg. Let's factor out the L, 1 minus 1/2, and cosine of theta will make square root of L squared minus x squared over L. Okay, cool. So that's that. And so the total energy, so the max energy we're going to have is the sum of those two. So it's going to be 1/2 kx squared plus mgl minus 1 minus 1/2 square root of L squared minus x squared over L, like that. Okay. All right, so suppose the person displaced the board by a smaller displacement, x2 less than x. Would the period of oscillation increase, decrease, or remain the same? Well, let's look at this. The x is really about L sine theta, right? So, because we don't have x especially directly in here. But actually, if you look at this period, it does not seem to depend on, well, the L's not going to change. Spring constant, yeah, it's not going to change. It remains the same, right? So it's independent of that displacement, right? So it remains the same. And the period equation does not depend on the amplitude x. Okay, cool. All right, let's look at gravitational one. This is kind of interesting one to do oscillation with a gravitation. Fold in a little bit of planets. This is what's going to make the AP Physics C exam hard, is to mix some of these things in. So we have a spherical non-rotating planet has a radius r, uniform density rho. Throughout its volume, suppose a narrow tunnel was drilled through the planet through diameters as shown in the figure above, which is small mass could move freely under the influence of gravity. Let r be the distance from the ball to the center of the planet. Express all your algebraic answers in terms of m, rho, r, big R, and fundamental constants. I think we need a mass. Oh, yeah, or we can do the density. Show that when the mass is released, it will undergo simple harmonic motion. Derive an expression for the period. So this is, again, now we're probably just going to use forces, so we want to set this up, right, is negative omega squared x. This is the differential equation we want to get to, right? So we're going to do F net equals ma on this one, right? So this is the equilibrium position. At the center, the force will be 0. And so the only force we have is force of gravity. So we're always going to do F net equals ma. And this force of gravity, if we say right is the positive direction, this force is going to be negative, right? So the force of gravity is going to be G, mass of the planet, m over r squared. Now this m is not the mass of the entire planet. From our Gaussian law for planets, we can only include the mass within the sphere here. So this mass is going to be the integral of the density times the volume, and we want to think about what we want to construct. Because it's as a uniform density, all that matters is the total volume. Okay, so that just becomes easier, and we just want to know what the volume of that sphere is, and that's going to be rho 4/3 pi r cubed, not big R, not the entire planet, just the part within this shell here, right? And so that's going to be there. So it's going to be G times rho 4/3 pi r cubed over r squared. So that's going to cancel and become R. And so that is going to be 4/3 G rho pi r. And so when we do F net equals ma, this is a negative force because it's pointing to the left. So it's going to be negative 4/3 G rho pi r. There still should be a little m here. M equals m times the acceleration. If we call this r, then this is going to be the second derivative of r, the position, right? Because we're just playing r with x. The m's cancel. There's an m on this side. It cancels with this one. So this, we get this proportionality to r. That's what we want. So our omega squared is going to be all these other values in here, which is going to be the 4/3 G rho pi. And so omega is going to be square root of that. So this is showing it. This setup right here shows harmonic oscillation because it's a restoring force that's proportional to the displacement, right? And then we're just now finding the period is 2 pi over omega, which is 2 pi, and then you just do reciprocal of this, 3/4 G rho pi, like that. Okay. Derive an expression for the speed of the mass as it goes through the center of the planet. This is going to be conservation of energy. We're going to talk about how much gravitational potential energy here has. We have velocity 0 at this point, so no kinetic energy, and that will get converted into full kinetic energy at that point. So the gravitational potential energy is going to be negative Gm, big M, little m over r, which is negative G, and we calculated the mass already, which is rho 4/3 pi r cubed times little m over r. That becomes r squared. So it's negative G rho 4/3 pi r squared m is the potential energy at the start. So that's our initial energy. And then at the equilibrium position, we're going to have kinetic energy plus any gravitational potential energy. That's going to be 0. So let me think about this. Why is it that we have... let me think about why it's negative. Oh, sorry, I'm making a mistake. We can't use the gravitational... this is assuming that the force is 1 over r squared. We have to actually figure out what the gravitational potential energy is, and probably... the easiest way to do this one is maybe just doing the work as the change in energy, actually. So there's a couple ways you can do this one, but we can't do this because the gravitational potential energy for planets, negative G m1 m2 over r, assumes that it's like you're going outside of the planet. Once you're inside the planet, it doesn't really apply. So we really want to think about this force of gravity here and just think about it maybe as it's doing work on it to give it kinetic energy. Like there's no kinetic energy, but we want to think about that force, that gravity, because we've already calculated the force of gravity. So the change in energy is going to be the work, which is going to be the integral of f dx, which is, again, the integral of the force of gravity. Force of gravity, we said, was G rho 4/3 pi r times m. And then dx, and we're going to integrate this. Actually, we'll just call it dr because we didn't call it x, we called it r. And we're going to integrate all the way from r to 0. Now, it's actually going to be, it should be a positive number at the end of the day because it's doing positive work because the force is pointing this way and the displacement is that way. So we might get a negative number if we do this, but it should still be positive. So we just got to make make sure that the sign is positive at the end of the day. Yeah. I think it's because we're integrating in the negative direction. So that's because we're going from right to left. So technically we go left to right, but that's okay. So we'll put a negative sign just to make this thing positive. So this is going to be g rho 4/3 pi m, and this is going to be r squared over 2 from 0 to, well, it's going to be from r to 0, but we're going to make it positive. So so plug in 0, you get 0. Plug in r, you get g rho 4/3 pi r squared over 2, which is negative, but we'll just make it positive. So the maximum kinetic energy we're going to get is going to be this guy. It's going to be, let's see, it's going to be 2. So it's going to be 2/3 pi g rho r squared, like that. Okay, so that's the maximum kinetic energy. Oh, that's not our total answer yet. We left out an m still. And that has to equal 1/2 m v squared, v max squared, the maximum speed. The m's cancel. Oops. We're going to multiply by 2, so we get 4/3 pi g rho r squared is equal to, and then square root of that is going to equal to the velocity. Okay, if the mass is released at a distance r, time t equals 0, write an equation for the acceleration as a function of time. Assume the mass is located. So here we just want to make sure we have a connection. So A, we're going to start with our cosine of omega t plus phi. Now at time 0, we know that x is equal to r, so the amplitude is just r cosine. And the omega, we actually solved for here. It's going to be square root of 4/3 g rho pi, g times rho times pi, t. And because this already at time 0, this is just a shift. At time 0, we're already at plus r, so we don't need to add any phase shift. So that's x. So then the velocity is the derivative of this, which is going to be negative r square root of 4/3 g rho pi by chain rule sine of that. And then acceleration's the derivative of that, right? So another one pops out and it becomes cosine negative r times 4/3 g rho pi cosine of square root of 4/3 g rho pi t. Okay, and so that would be our acceleration here. Okay, and then kind of an interesting thing just to note to connect to the previous one, we found that the maximum speed was here. You could have done it this way. Look at this. This is the amplitude right here, right? This is V max, right? Because it's the amplitude of the sine. And if you take the square root of r squared, you get r, you get the exact same answer here. So it actually happens to be the same thing. Probably an alternative way you could have solved for b to find the V max is to find the expression for the velocity using the harmonic motion equation and then just take the amplitude directly. That would have also worked. And it just occurs to me now after I'm doing part C here.